journals. So with these few words, I welcome Mr. Siddharth to give the guest lecture on applications of computational fluid dynamics in fire safety engineering. Thank you.
Right. Thank you, sir. I hope everybody can hear me fine, and a very good evening to all of you. Hope you're all doing well in this COVID situation. So I'll begin to share my screen. Once you are able to see my screen, please let me know. So. Uh, So if somebody can give a thumbs up once they can see my screen, or tell that you can see my screen, it would be
Yeah, your
fine.
screen is visible, Siddharth.
Okay,
We are able to
perfect.
see your screen.
Yeah, perfect. Right. So I'll go right ahead and start the presentation. So off the top, I'm actually taking over for a friend of mine who is just not able to give the lecture today, and so instead of him, I'm doing it. So yeah, that's the thing. And so the topic for today is it's a very brief introduction to computational fluid dynamics and some applications, how we can save buildings from fire. So and its application in fire safety engineering. So that is one of the main topics today, and I'll be mostly going over to through the basics of computational fluid dynamics, which is the most part of this guest lecture. And since we have started like around 10-13 minutes late, I'll try to condense the stuff as quickly as possible and try to show you how to set up a brief simulation using ANSYS Fluent as well. And we can try to have a 15-minute interaction towards the end of the lecture. I hope the plan is fine. So in this title, whatever text you see in red and blue color are the ones you want to read. And the one in green and black, it's not something that you're compulsorily required to read or all that. It's just for the purpose of information, and it's not a point to take home. So going to the next slide, the synopsis of what I'm going to be covering today. So I'll start with what is fluid mechanics and heat transfer, and I'll go through some very basic mathematics in CFD, and then the conditions that are to be satisfied to solve a problem using CFD. And then I'll go over what is known as the simple algorithm. So that was one of the first algorithms developed to solve a problem using CFD. And then using ANSYS Fluent, it is one of the commercial softwares that is used widely by a lot of companies to solve problems in CFD related to fluid mechanics and thermal engineering. And then finally, the points that we are going to be taking home, the applications and the conclusion. So why do we want to do CFD, all that. And then, can anyone volunteer and tell me what exactly a fluid is? Anyone? It can be a staff, it can be a student, anybody. What is a fluid?
A substance which keeps on deforming continuously.
Yeah, okay. And how is that different from a solid?
Solid will not deform freely, whereas fluid
Yeah,
will deform freely.
yeah, even for the smallest amount of force. So yeah, smallest amount of shear force. So yeah, that is the thing. And then heat transfer is a form of energy transfer that takes place as a result of the temperature gradient. So could yeah, once again I want some volunteers. Could anyone tell me the difference between thermodynamics and heat transfer? Because if you split thermo and dynamics, it's almost heat transfer. But yeah, if anyone could find the difference, you might be able to crack interviews. So
Students, please unmute yourself and
yeah, I mean, you don't have to be shy or anything. I'm not going to punish you if you're going to say the wrong answer. So please feel free. So Yeah, no issues. Heat transfer gives us an estimation of which direction in which the process takes place, uh, and how much time it requires for a particular process to take place. Especially if the energy transfer is through heat, how long does it take, and what form of heat transfer is going to happen for that particular process for achieving a steady state in the end, because our nature does not like extremes. It likes to balance things out. That is why if you have something at a very high point, and if you, for example, if you're on the top of a building and you have a ball over there, and if you push the ball, the energy of the ball is very high. That is why it falls down to the ground where the energy level is zero. This difference in energy is this falling is because of difference in potential energy, and heat transfer simply takes place because of difference in temperature. So wherever you have any sort of difference, if it is voltage, current will flow. If it is temperature, heat will flow. So if it is pressure, a fluid will flow. So all of these are analogous. And for fluid mechanics, we have a set of equations known as the Navier-Stokes equations, which is nothing but Newton's second law applied for a fluid. That's it. So force is equal to mass times acceleration. That is the formula that is being used to solve fluid mechanics problem. However, there are a lot of different forces. So in a fluid, if you a fluid obviously has viscosity, so it will have viscous forces, and if it is under the action of gravity, it will have gravity body forces and a lot of other forces and different sources of acceleration on the right hand side. F is equal to ma is what I said. So F is different types of forces and A is different types of acceleration. So clubbing all of these together is what CFD is about. This basic equation is what is being used to solve computational fluid dynamics problems. And the difficult portion of this is that you don't have an analytical solution, meaning you cannot take out pen and paper and start deriving an equation and find the solution for it. It's not possible. So uh, it requires computers. There is no other choice around it. And if any person is able to like analytically derive and solve and find a solution, that person is going to be given a Nobel Prize, because it is one of the most difficult problems in physics. So it's astonishing how a simple formula like F is equal to ma is able to do this much. So we have to thank Newton for I mean, almost everything, all the applications that we have today, our air conditioners, our fans, our exhaust fans, are anything that works, anything that needs heat to dissipate. Even your mobile phones or laptops from which you're watching, it has a fan or a copper plate that is conducting away heat. So almost everything comes and boils down to CFD. All these applications are there. So the next question is, what is a transport phenomenon? This is not something we might have encountered in a BE degree. So it is basically moving something from one place to another. That is the English definition of transport. For fluid mechanics, we have three things like that. One is you can transfer mass from one place to another. You can transfer momentum from one place to another. You can transfer energy from one place to another. So all of these three interactions are what make a transport phenomenon possible, and that is what we'll be solving for our problems in CFD. I'm not going to be very mathematical with the mathematics that I've said. So there are three different methods in which you can solve a computational fluid dynamics problem. So in your 6th or 7th semester, depending on which regulation the students are there, you would have learned finite element method. Mostly this probably third year students are higher. And this method utilizes something called weighted residuals, where you initially guess one solution for a differential equation. You will just guess. You'll say, okay, I'll use one linear equation simply. Linear equation means, let's say y is equal to x. That's all. So there is one line. Linear means there is just one line. That's all. So for that linear first order equation, you will say, okay, I am choosing this. And then what you will do is you will modify the question, that is the differential equation of interest, and you will add something called a weighted residual and try to solve this problem using various methods. So it can be Newton-Raphson, that is iterative method, or you can form something called a stiffness matrix, uh, whose short form is again force is equal to stiffness into displacement. So you will bring all of these difficult terms that I told you earlier into just these three terms, and then you will try to solve either the force or the displacement, because the stiffness is mostly associated with the material property. So that is finite element method. And the other two, finite difference and finite volume method, are almost similar, and those utilize the principles of just this Taylor series expansion. So what you can see here. So basically, if you're trying to solve one equation, uh, this terminology may be confusing, but this is simply dy by dx. If you're different, df by dx rather here, since the function is named as f, the term here is df by dx, and this is d square f by dx square. And similarly, it goes on to higher orders. So if you want a first order accurate solution, first order means the power of the differential is 1, meaning differentiation is done only 1. So df by dx. So this is first order solution. So if you say, for me, my solution, it is enough if I have 1, then you will not expand after this. If you want second order, which is mostly what is used in the industry, this is more than enough to be accurate, these equations. So what you will do is you will just have these, substitute whatever known quantity you have into this, and then it is only algebra. You will just take the unknown quantity to the left side and try to find what is the known quantity on the right side. That's it. So this basic algebra is what contributes to finite difference and finite volume method. So the order of accuracy is dependent wholly on the user who is performing the simulation. So having said that, I will go to the conditions that are required to solve a problem. So once, I mean, even people who have studied CFD in their courses tend to forget it while doing a simulation. So in their mind, they'll start saying, "Idu namakku theriyama poche, namakku thonama poche, nama marandutome." All that feelings will start coming. So basically, since I said we are using an approximate differential equation, meaning we are stopping somewhere here, we need to see if that approximate equation is having its error reduced as once we go on adding terms to it. Meaning, first order accurate means it's like accuracy is only up to this much. So naturally, adding more terms should improve the accuracy drastically, and it should come to the analytical function that we want. So this can be anything. So this is just a Taylor series expansion that is generic. It can be, if you want to find temperature, you can do it in the same way. If you want to find what is the pressure, you can find it in the same way. All you have to do is substitute the relevant terms in this portion and modify. So that is how the stuff is. And so basically, if you increase the order of accuracy, does the error approach 0? That is what is called as a consistent equation. And then stability. The meaning of that is if you have that's again what do we call, the error should reduce as the simulation gets performed, meaning the process is iterative. That is why we have a lot of iterations in simulations. And you would have encountered this in the 4th maths paper, where you would have done a lot of iterations in Runge-Kutta method, Newton-Raphson method, and all that. So basically, your error should start going down once you perform a lot of iterations. That is the meaning. If it starts to increase, if the error starts to increase, then there is no point in doing that. So you'll say that my solution is not getting arrived at, it is getting diverged. So your solution should be stable, and you should not get any abnormal values as you solve the simulation. So that is the second one. Then the third one, convergence. So this is true if uh, your solution approaches the true solution. What do you expect? So if you try solving something analytically, for that you will have one particular solution. If you say x minus y is equal to 1 and x plus y is equal to 2, then if you add both of these equations, you will say x is equal to 1.5 by just adding all of that and find the value by substituting 1.5 for in the equation. So you have excuse me, two equations and two unknowns. So you're solving simultaneous equations like that. But if you were to solve that iteratively, you would go with a Gauss-Seidel method, and you'll start like putting a diagonally dominant matrix. I am pretty sure the students who are in the 4th semester should be able to link what I'm saying with this. So Gauss-Seidel method, with that you can actually try and calculate the values of x and y iteratively. So if both of these are same, then the solution is converged. That is the thing. So putting all of these terms together, there is one theorem called the Lax equivalence theorem. So they say that when a finite difference approximation for a partial differential equation is consistent and also stable, then it should definitely converge. So that is the equation. So if you have consistency and stability, then convergence is not an issue. So if you don't have convergence, then you need to check what is wrong with it. So that is the point. And then this is a little tricky, but I can try to explain it without mathematics using just these items in the flowchart. So these algorithms are what are used in commercial and also in-house CFD software. And the first algorithm that was developed was known as the simple algorithm, and it stands for semi-implicit method for pressure-linked equations. So the meaning of an implicit equation is any equation will have a left-hand side and a right-hand side. So I said y is equal to x plus 1. You're able to say y in terms of x completely. But if my equation is something like log of xy is equal to xy plus 1, and it is something like this, you're not able to put y on one side of the equal to symbol and x on the other side, then that equation is called an implicit equation. It definitely needs to be solved iteratively only. There is no choice. So that is implicit equation. And the next one, PISO, pressure implicit with splitting of operators. Again, that is another implicit equation. So what one needs to know from this is generally used for steady state simulations, meaning there is no time dependence for it. If you try to solve something, it is independent of time. And for PISO algorithm, it is generally used for transient simulations, meaning it is dependent on time. So any process, for example, I am starting to heat one box, let's say, it is going to take some time for it to reach its maximum temperature, and then it will stabilize based on the atmospheric temperature, and then based on whether it has a heat sink or not, or something like that. So based on what the external conditions are, that is known as a boundary condition, and whatever heat you are giving, that is known as a source condition, and whatever object is being heated, that is our computational domain. So these are all the terms being used. So what will happen is once it attains steady state, it's going to be constant. It's going to be a flat line. That's it. So that region, if you're simulating, then that is a steady state simulation. But if you just begin heating, what will happen is its temperature will slowly start to rise, and then it will go and stabilize. So this rising portion is, if that is your interest, then you have to perform something called as a transient simulation, meaning it changes with time. So what does the simple algorithm do? So remember in the starting, I said momentum, mass transport, and then energy transport. Let's get into that. So there is something called a momentum equation, that is our Navier-Stokes equation. So you will solve the momentum portions alone. You will solve just the velocities in the first step. Then you will solve an equation for corrected pressure. So whatever step I have written here, these are the equations for it. So assuming one pressure, you will calculate the velocities. That is the first step. Then after that, you will try and correct what the velocity is and the pressure is using a subsequent steps. And then if you have heat transfer, you will solve the other equations. Otherwise, this portion is not there. Then once again, you have to like correct pressure and velocity. So for flow, you have something called continuity, and then you have momentum. So what you will do is you will find something using continuity, put it into momentum. You will find one value. Find that value you will take and put it back into continuity. You will see whether both of these are equal. If no, then you will repeat. That is the point. So basically, you're calculating one thing using one equation, substituting in the next, seeing if both the values are equal. If it is not, then the cycle repeats. And once the both of these equations are satisfied, both continuity and the momentum equations are satisfied, and then we'll call the solution as converged. That is the point. So this algorithm will help us do that. And there is also another thing called coupled, where these two steps are solved together. That is the latest method in the solvers, whose mathematics is a little difficult even for me to understand right now. So it's going to take a bit of reading, but it's definitely interesting. And then this is one example problem. Let me not do this. I'll go out and then I can show you guys what I did with the simulation. So basically, I'll try and open up the geometry. Hopefully, this shouldn't take a lot of time. So what you will do is basically you will draw a pipe. This gray portion is a pipe, and you will extract the fluid flowing through the pipe inside, which is a solid cylinder. And then you will say, at the inlet, my velocity is this much. And then at the outlet, my pressure is open to the atmosphere. So the gauge pressure is 0. So because of velocity here, it will have higher pressure here and a 0 pressure here. So from what I said in the beginning, the difference in pressure is going to make the fluid flow. So that is what is happening. So how do we verify using whether our result is correct from the simulation that we are getting? So for that, for simple stuff like this, you will be able to do stuff analytically. So if anybody can name what this equation is, please tell me. What is this equation?
Hagen-Poiseuille equation.
Yeah, correct. So that is the equation that is used for solving for laminar flow. For turbulent, we use the what do you call Darcy Weisbach, and then for that you will require the friction factor to be taken from empirical formulae and stuff. So basically, this is my geometry. So I have my gray pipe, and inside which I have this translucent fluid. So I have made one small extrusion to account for something known as an entrance length. So what is entrance length? I have put the picture here. So anybody who is able to see can easily interpret. Right, I'll tell it myself. So it's basically where the velocity profile becomes fully developed from the region of developing flow to fully developed flow. So a parabolic velocity profile for a circular pipe is when the entrance region is fully complete. What will happen is at the inlet, you will have a uniform velocity profile, meaning wherever you check the velocity, it is going to be the same. So suddenly, if it comes in contact with the pipe, what will happen is the velocity near the wall will become 0. And then subsequently, it'll start to compensate by increasing the velocity in the middle, because no object tries to adapt itself to the external surroundings immediately. So that is Newton's first law. Any object in motion will try to stay in motion, and any object in rest will try to stay in rest. So if you're suddenly bringing something near the wall to rest, what it will try to do is try and compensate it in the middle. So it will increase its velocity in the middle, and at the walls it is going to become zero, such that at any section the energy is constant. So that is what it is trying to do. So by Newton's first law, you will have an entrance length. So that is there. And once you are modeling, you're going to divide the entire domain into extremely small parts known as a mesh. So this is where we will be solving the Navier-Stokes equation. And it is going to be solved in the methods that I was describing using all those complex mathematical terms in the previous slides. So since the domain is very small, these algebraic equations are more than good enough to compute what the values of velocity and pressure are going to be. So if you do a CFD simulation in a company or anywhere, this is how you will almost be presenting stuff. So if it is a simple problem, you are going to be showing what the boundary conditions are. This is the dimensions of the pipe that I've drawn. This is the inlet velocity, and I've used water. So the properties, the density, the viscosity, and what I'm trying to find is the pressure drop. So what is the difference in pressure between the inlet and the outlet for this particular flow, for this particular velocity? So as you can see, it is 0.2 if I use this equation and find out. It is 0.17 if I use CFD. So probably I need to work more on refining my CFD problem to try and match it with 0.2. That is the thing. So this is what you will try and do as a CFD engineer in a company also. So what you will try to do is you have to try and benchmark your simulation. It's not just pressing buttons and drawing stuff. You have to know why you're doing also. So all those things are what is generically being done. So the next problem is an example I've shown using heat transfer, where this is Nusselt number. So it's h d by k, and for a problem with heat transfer at the walls with constant heat transfer, the Nusselt number is a constant, and this is a very specific case. The flow has to be laminar, and the flow has to be fully developed, and you should have uniform heat flux on the walls. Only then the Nusselt number is 4.36. So using that, you will try and find what is the heat transfer coefficient for the flow. So since my flow is in the developing region, the heat transfer coefficient is higher than it should be. And using the formula over here, if I try to find what the heat transfer coefficient for this is, it's going to be much lower because the flow hasn't fully developed yet. But once the flow is fully developed, both of these two are going to match very well. So you should take all these things into consideration before trying and solving a problem. So I'll go directly to results. So in this mesh, you will do a mesh, and this is where inside the setup is where you will set all the boundary conditions in ANSYS Fluent. This is the solution, and you will have the results. So the results is where you try and extract all these pictures from. So that is the goal. So since we are short of time, I'll go to the applications directly. And if there is time towards the end, I'll try and show one simulation at the end. So coming to the applications of CFD, it's basically everywhere you see heat or something flowing. So the human body is one good example. And the company that I'm working in right now is dealing with medical devices. So if you want to analyze flow through a syringe, or people might have encountered blood donations and stuff. So flow through the small tubes, flow of blood into the tubes and all that is what I deal with. So the human body. And then our air conditioning systems, it has a lot of refrigerant flowing. There is also a compressor, and we have an exhaust fan and all that. So it's a fairly complicated device that has both heat transfer and fluid mechanics coupled together. And then in electronics, so our electronics is where it generates quite a lot of heat flux, meaning For the area it is mounted for such a small chip, it is going to generate a lot of heat for its size. So naturally what will happen is the temperature is going to shoot up. So how do we cool it down? For example, for a chip, if the temperature goes above 160 degrees, it's going to explode. So nobody wants that. We need to try and cool it somehow. So how do we cool it? So you'll bring in your knowledge of heat transfer and try to model something like a heat sink to cool the electronics. And then there is obviously a car radiator. So almost all automobiles are going to use CFD because it's not just the engine, it's the aerodynamics of the car and all that. So the applications in automobile is without question going to use a lot of CFD. And then thermal power plants, nuclear power plants, and refrigeration systems. So that is there. So coming to the point of today, so how is CFD being used in fire safety? Can anybody tell me what a fire triangle is? Or what are the necessary conditions for fire to happen? Anyone? I'm not able to hear you properly. Could you repeat?
Fuel is an ignition.
Am I audible
Oxygen, fuel,
Oh.
oxygen, fuel, and fire.
Okay, oxygen, fuel, and okay, you got two of
Fire.
those correct. It's not fire, it's heat. Basically, you need the fuel to achieve ignition temperature. So you need heat. You should basically, for a diesel engine, you don't have a spark plug, so you don't have fire making fire. So basically, if you make something go to that temperature, and if you have sufficient oxygen and the fuel, it is going to make fire. You are close. Good. So for extinguishing fire, what you need to do is you need to cut off any one of these. That's the ultimate goal. So if you cut off oxygen, fire is not going to happen. If you cut off the fuel, it's not feasible. It's difficult. So you can, most of the applications are going to revolve only around cutting of oxygen and the heat. So what you can do is in a building, you can simulate what potential areas might catch fire, and with that computational domain, meaning you can model your entire room in CAD. I have modeled a pipe in CAD. You can model an entire room in CAD, and in that room, you can say from where the fire is starting, and because of what the fire is starting. Basically, we are trying to analyze, for example, if there is some combustible material over there and it is reaching that temperature. So if fire starts from one particular point, how is it going to propagate inside my room? I will be able to simulate that. So we do something called a large eddy simulation for that. It requires a good deal of computer power. So with that, you can say, okay, my fire is going to start from this direction and go towards this direction. So, and also you can estimate how the smoke from the fire is also going to move using CFD. So using that, you can say, okay, I can place my exhaust fans here. I can place my vents here. I can place my fire extinguisher here. So all of those strategic plannings can be done using CFD. Although all of this is relatively new, because it requires extreme computational power for doing such a difficult simulation. Because it involves a chemical reaction as well as fluid mechanics as well as heat transfer. So the examples I showed you, this is just fluid flow. This is fluid flow with heat transfer. So now we are adding one more variable to it, and we are not doing it in a pipe. We are doing it in a very big room. So it's going to be very difficult for doing a simulation of that sort. And then what you will do is you will try and verify it using a scaled down model. So you would have all studied in fluid mechanics, assuming you're all second year or higher, about what is that called? The third chapter. What is the third unit in fluid mechanics? We'll study a lot of non-dimensional numbers and all that to compare prototypes, models, and all that. So that is the chapter that we are dealing with here. So you will have a scale
Dimension
down.
analysis.
Yeah, exactly, dimensional analysis. So the what you're going to be doing is an application of dimensional analysis where you're scaling down the entire model, and you're going to be analyzing how it is happening there. This is an experiment, so you want to verify whether the predictions you've made using CFD are correct. Without that, it's very risky to do in a real building. So what you have to do is always try and compare CFD with something you already know, because as accurate as CFD is as accurate as the analyst wants it to be, because the choice is yours. You can make it as accurate as you want it to be. And if the application is very critical and I say, okay, first order is enough, then if the result is varying by 50%, then people may end up dying. So whatever work we are doing, we are supposed to compare it with an experimental result or something that we already know, so that we are confident enough with the CFD simulation that we can directly go into the application. So that is one disclaimer always. CFD is never a substitution for experiment, but it's merely a complement, and that's what I would have told in conclusion. So computational dynamics, fluid dynamics comes in between a pure experiment and pure theory, because if you want to go and perform an experiment for everything, it's going to be very costly, and it's going to be prohibitively costly. You cannot spend crores and crores just for different prototypes. No, this design is not working, this design is not working. You cannot go and make more and more prototypes. That is where CFD comes in. You can make all of the changes in the CAD and then analyze whether my result is good enough or not. And similarly, our pure theory is for extremely simple cases, like the Hagen-Poiseuille equation is just for a cylindrical pipe. Beyond that, you cannot derive also. It's very difficult to derive for a square pipe. Try with a square, it's not possible. It's going to be difficult if not possible. So a pure theory is limited to only very simple geometries, and hence that's not going to be helpful for real world applications that much. And then this is where CFD comes in. So it's going to take a little bit of both, and then try and solve the problem, try and address the problem. So for this, all you need is a good computer. So instead of spending crores, you're going to be spending lakhs, because ANSYS costs around like 50 lakhs if you want to take the entire package of structures and also fluids. And an experiment would cost crores each time you do it. And with this 50 lakhs simulation software, you can basically keep on doing simulations as much as you want. So it's not that costly for a company to invest in CFD as compared to an experiment. So that is where CFD is coming in. And it's also an emerging area in India. So that is one thing. And these are the references from which I put together my slides. So you can all read this whenever you get time and if you're interested. So Fluid Mechanics and Applications by Cengel, Heat Transfer by Cengel, NPTEL, and then CFD by John D. Anderson and the ANSYS Fluent Manual. So that is there. Thank you. If there is any question or anything, you can let me know. We have 10 minutes, so I have time.
So students, if you have any question, you can ask the speaker. Students, feel free.
Yeah,
If you're
anybody can
seeing
ask. Yeah, anybody
you
can
can
ask.
ask your questions regarding
தமிழ்லையும்
CFD.
கேட்கலாம்.
No doubts.
தமிழ்லையும் கேட்கலாம், தப்பு இல்ல.
சொல்லலாம். Yeah, yeah.
தமிழையும் கேட்கலாம், தப்பு இல்ல, ஒன்றும் பிரச்சனை இல்லை. என்னடா 6:30 மணிக்கு வந்து உட்கார வச்சுட்டாங்களேன்னா ஃபீல்லாம் பண்ண வேண்டாம். It's useful. So if you learn all this, it's going to be helpful for your career also. So if you're interested, that is.
Third year students, you can ask a question because you are studying FEA now.
Yeah, anybody. If it can be generic also. It doesn't have to be, what do you say, completely related to the presentation or something. You
Yeah,
can
yeah.
ask any
Yes,
generic
that.
stuff also. So. Staff also can ask, by the way. So எல்லாருக்கும் எல்லாம் புரிஞ்சிருச்சா? இல்ல யாருக்கும் எதுவுமே புரியலையா? சவுண்டே காணோம்.
Siddharth, can we have a modeling like that is for in FEA we'll be using the equations. For instance, if you want to find a displacement of an object, and there we are going to discretize and have some 36 elements. Let us say we are going to do a analysis on an axisymmetric element, and suppose we are discretizing that into some 50 elements. Like in those times, for that we cannot use the manual method.
Correct. We need to
I
use
saw a
MATLAB.
method where people are using that is theoretically they were solving by using the same equations what we use for one-dimensional element by having one element, right? They are using in MATLAB. So likewise for CFD, do we have MATLAB? We can run MATLAB codes and can we compare that thing?
Yeah, you can run it in MATLAB. There is no doubt at all. So I have a few courses that I did using MATLAB. You don't even need MATLAB. You can do it in Excel itself. All you need is just an equation. So this Excel is for something.
In MATLAB, what I saw was I was looking for an anisogrid structure. That is one of my friends is doing research in that. So when I was just he asked me that kind of help. So when I was surfing through the net in a YouTube, I saw a YouTuber who was performing an equation. That is, he was very particular about 1 to 50 element. He was creating a stiffness matrix for each and every element, and then he was getting the displacement for the diagonal grid structure.
Okay.
So there he used a for loop and other things while writing the MATLAB code. So for that simple, it was like a simple. That is, we know if we have 2 element, we manually will do that by forming the stiffness equation, and then we will use the force equation F equal to KU.
Correct.
But it was very surprised that that was being performed for. So likewise for a CFD, for CFD there are non-linear type of.
Correct.
Yeah, that's it.
Yeah, what you can do is you can solve very simple. You can don't go for 3D. You can do 2D. And here, this particular simulation is a 1D rod.
Okay.
So for that, we are giving what is the cross-sectional area of the rod, what is the length of the rod, what is the temperature at the left, temperature at the right, and then we are having one internal heat generation. And we are having one fluid density, fluid viscosity. All these are just the inputs. So basically, you are saying, I want 5 cells. These cells are spaced 1 mm apart from each other. And then in each coordinate, you're saying where it is placed. These are all the x coordinates. And then you're saying the x coordinates of the centroids everywhere. And all that, it is being computed. So you can very simply develop this code using Excel itself. You can do the same thing in Python. You can do the same thing in MATLAB, everything. And the final result is over here. Just these are my inputs. For this, I'm getting, left side, I'm saying 100, right side 200 is the temperature. In between, what are all the temperatures? This is what I'm about to find, and how it is varying, the trend, and with respect to the distance. So you can do a lot of this in Excel itself. So yeah, once we begin.
No, my doubt is that there we'll be using array command for the matrix, right?
Yeah, here we have the matrix here itself. Excel, what you can do is see, the A matrix is like this. This is a square matrix.
Yeah.
So
you are giving it in the sense of that is
correct.
A 4 cross 5 cross 5.
Yeah, Excel has this command.
It's very good.
Excel has this command where you can say M inverse, meaning matrix inverse. You are inverting the A matrix here. What is the inverse of this matrix?
Formula bar f of x.
Correct.
There.
Yeah, that's it. You can just type the formula and say, from this cell B38 to F42, I want my matrix to be inverted. The only thing, everybody will know is that you need a square matrix. That is the main thing. And you will have a vector. So this is the temperature vector. That's it. It's very simple. So
Super.
in Excel, it's extremely easy to do stuff. You can just say M inverse. That's all. That is the command you want to use. Nothing else.
Oh,
Over there in
then we
MATLAB,
have to
what you can
locate the cell where it is going to start and where that is left corner and right corner.
corner. Correct. Yeah, that's it. And all
Super,
of those
super.
details are
Yeah.
here. That's it.
Oh, very
So
good, very good, very nice.
yeah. And the commercial software will take it up even to a higher level, because what I have done here is for a very regular geometry. It's just a rod,
Okay.
so you can split it into 5 equal pieces. But for
Yeah.
our simulations here, for example, this cylindrical pipe, in order to
Okay.
I'll make this picture bigger, so
Hmm.
it has
Okay. What
Tetra.
about the computation time? There we have much more element. We have fine mesh.
This is a very simple problem, so it takes less than 30 seconds to solve. That is not at all a problem.
Super, super.
Yeah.
But
So
complex problems will take much more time, right?
yeah,
When we are
yeah,
solving
correct. Yeah,
in Excel.
some of the problems that I have solved can go up to even 5 days continuously. So all
Yes,
you will do
yes.
is just give run for the simulation after verifying it, and then it will
Hmm.
go on for 5 days also. The transient simulations that I was talking about, the one that is run with respect to time, it is going to take a lot of time. So
Oh, fine. For simple geometries and for simple problems,
yeah,
you can use Excel. But
yeah,
for complex things, we have to rely only on the commercial softwares which are
yeah,
available, right?
either commercial, or you can there are open source software also, like OpenFOAM for this. FEA you can pretty much I mean, it's only dependent on the effort we are willing to put. For example, if you want to solve a complex problem using Excel itself, we can do, but the thing is, it's going to take a lot of time.
Lot of time, yeah.
Yeah.
Because even ANSYS solver, when we are going to solve a problem on a crash analysis,
Mm.
so even that takes much time.
Yeah, it'll
Like
take
some
8-9
5
hours.
hours, yeah,
So yeah,
yeah.
that'll take 8 to 9 hours.
Because
Yeah.
the Illustrator doesn't have it doesn't have a solver, but what we do is that we will use ANSYS solver for following
Mm.
for solving problems oriented with Illustrator.
Yeah.
Then
Yeah.
we have a
Nowadays,
separate thing, LS pre-post for
correct.
modeling the problem, and for getting the post processing, we have
LS
LS post.
post. Yeah.
There we'll just see the results.
Yeah.
Okay.
Since ANSYS has bought LS Dyna, we have that as our
Hmm.
thing. Yeah. So that is
Oh,
one
now
thing.
we have LS, ANSYS LS pre-post, right? Something like
Correct.
collaboration.
Correct. Yeah.
Yeah, when
ANSYS
we
has
were
bought that
studying,
company.
LS and was separate,
Yeah.
but
Now
it is not
ANSYS has bought
that
it.
much friendly when compared to
Yeah.
Former.
ANSYS
That
is
was,
easy.
yeah. There we need to know specifically what command and
Correct.
what is going to perform or what is going to function.
Yeah. So
Okay.
for
I think for
FEA,
composite also we have
yeah, we can do.
ANSYS composite. I think we have a package
Yeah, there
from
is a package.
18.2 onwards.
Yeah, 1 second.
Yeah. Yeah, one of the research papers I saw.
You can actually do composites in normal static structural itself.
Yeah, that
And
ACP thing will have on
yeah,
composites, I think.
composite. Yeah, this is
Yeah,
there.
right. This is, yeah.
And in our classic ANSYS, basically mechanical APDL.
APDL.
Yeah, in APDL you can solve all the problems, but for learning, that is the best, because with GUI anybody can operate the buttons. But
Yes.
if we do using APDL, that is the best way to go. So
okay, Siddharth.
yeah, so
Okay, any queries from the faculty side and from the student side?
Thank you. Thank you very much, Mr. Siddharth. It's really a very wonderful presentation.
thank you, sir.
That with a very short span of time, you have done excellently. The way in which you presented the communication, PowerPoint, everything is so attractive, like you.
Thank you, sir.
Thank you very much, sir. Thank you.
Yes, sir. My pleasure.
Yeah, thank you so much, Siddharth.
Yes, sir.
Because
No
it was
issues.
a short span in which Mr. Sundar was not able to due to his personal reasons. Yeah.
Correct. Yeah.
So thank you very much for accepting our invite
Yes,
and delivering
issues.
a wonderful lecture on the CFD. That in this short span, you give a very good glimpse of idea depending on the audience and what they require. and it was an excellent session.
Thank
So thank you so much. On behalf of our department and behalf of our college, we thank you for this wonderful session.
Yes, sir. You're welcome, and yeah, hope to see everyone around soon. Yeah, take care.
Yeah, thank you.
Thank you, sir.
Sir, shall we end the session,
Thank you,
sir?
Yeah. Okay. Bye-bye.
Pradeep sir, do you want to say anything, sir? So Pradeep sir?
So, no, sir, it's fine. I had a good session of introduction. Actually, we had a nice session of all those things. Nothing else to say, sir. It's okay, sir. We can end up the session. Thank you, sir.
Yeah, okay, sir. Thank you, sir. Thank you, sir. Thank you, Siddharth.
Right. Thank you, everyone. Yeah, take care. Bye.
Yeah, thank you.